We're doing some work here with a circuit with a switch in it, connecting power, figuring out how the current flows, things like that. Okay, so first we want to know if the total current will be greater in position A or position B of the switch, and we want to do that, try to do that without calculating anything. So in position A, the current is going to flow through here, and then down through A, through this resistor and back. Position B, it'll do much the same, except go that way at the junction, and then come back. So in both we have this 400 ohm resistor, but in position A we have the 2K, and position B we have the 1.2K. Those are in series, so if we're in position A, the equivalent resistance is much higher. So a higher equivalent resistance means a lower current given the same delta V, right? So we're assuming that there's the same battery on both of those. If you have a circuit with higher equivalent resistance, it will draw less current from the same battery. Alright, so without having to calculate, we get that, and later when we go and calculate things, we would want to check that out, make sure that that was the same. This is an SPDT switch, single pole, double throw. So the throw is between these two things, and there's only one of them, so it's a single pole. A DPDT would be basically two of these side by side that both flip together. We want the power dissipated when the switch is in position B. If the switch is in, we can do the whole chart. So I guess I'll set up the chart. We don't need to actually solve the whole thing, but we can set it up. So we have a 400 ohm resistor, we have a 1.2K resistor. I'm not going to put the other one in because no current flows through it, so it's like it's not even there. Now those two are in series, so the total resistance will be 1.6K ohm. Across the whole circuit we have to lose the whole 10 volts, which means that our total current is our total delta V over the REQ, which would be 10 volts over 1600 ohms, which will be 6.3 milliamps. Now this is a series circuit, so there are no branches, so that current has to be the same throughout all the elements. And now I can just do IR for these to figure out my voltage changes. So 6.3 milliamps times 400 ohms. We're going to get about -2.5 volts here, and then about -7.5 volts here. If I look at the loop rule, plus 10, minus 2.5, minus 7.5, that does get me back to 0, so that works. If I look for power, I guess I said we weren't going to solve it, but we solved it. If I look at power, I'm looking for the whole circuit, so I'm going to take the whole thing as 1, so the current through that is 6.3 milliamps and the voltage is 10 volts, so we're looking at about 63 milliwatts, right? Power being I times delta V, so multiply these together, we get about 63 milliwatts. So that's what we're looking for that part. Next, we want to know how long it would take. Oops. Question just there we go. How long it would take for 11.7 megajoules of energy, which is the energy content of a Snickers bar, to be dissipated by this circuit. So if I know that the power, which is 63 milliwatts, power is energy transfer rate. So change in energy over change in time. I'm going to know my energy transfer rate. So that's 11.7 megajoules over delta T. So if I solve for it, delta T is going to be 11.7 times 10 to the 6th joules, that's mega, right, million, over 63 milliwatts, that's 0.063 watts. 1 watt is 1 joule per second, which means that the joules will cancel, the seconds being in the denominator of the denominator will go up, and I will get a time in seconds, which is good, because that's what I was expecting. But I want to check it out, because if the units didn't work, then I would not, my number definitely wouldn't be right if the units aren't right. I get about 18.6 million seconds, which is about 217 days, which is, a long time.